fulfill their desires. Set to waste of existence. Spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Set to waste of existence.
Anxious Earth is rising. Anxious Earth is rising. I'm so happy.
We spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence.
Hey, what was that? It wasn't supposed to happen. This is Double Tribble channel on Twitch. My name is Ron. I live in rural New Hampshire. This is a live stream. If you're watching this on a VOD somewhere, on a video, on YouTube, or on the website, doubletribble.com, this is a live thing. It's not a edited down video. But today I'm going to talk about space-time diagrams. I'm going to try to blow through it as quickly as possible and make it as clean as possible as we can for a live type broadcast. There are a bunch of different videos out there on YouTube and different places that talk about different things and teach you different stuff. I'm going to try to teach it to you live, which makes it a little bit more challenging, but that's how I like to do it. So if you're watching it live, there's going to be ads, and usually I pause when the ads come on, but I'm not going to do that this time. I'm mostly doing this for the VOD. I'm doing this for the video. If you're watching this on a video, feel free to skip ahead different parts, but actually I'm going to try to get this started as soon as possible. Yeah, give me a follow, all that stuff. You know the deal, right? All right, so the first thing I'm going to do, the reason why I'm doing this, let's let you know why I'm doing this space-time diagram tutorial here, is a little over a year ago, on September 1st of 24, I did a stream on special relativity. And if you don't know about special relativity, then you should probably watch that stream. It's on YouTube. It's on my website, doubletribble.com. September 1st, 2024. I did a thing. I talked about special relativity. And in that stream, I said, oh, one of these days I'll do the twin paradox. If people are not familiar with the twin paradox, it's a very famous thing that has to do with relativity, where a pair of twins are on Earth. One of them takes off on a rocket, goes away, comes back, and the one that went on the rocket is younger than the one that has stayed on Earth when they get back together. And there's a paradox associated with that. I said, oh, I'll do a stream on that, and it's been a year. So, and when I started preparing for the twin paradox tutorial, I realized that, well, people have to understand what space-time diagram is. And I noticed that a lot of people who do the twin paradox thing, try to explain it on YouTube, they don't explain what space-time diagrams are. And if you're not familiar with them, you may think that you know what they are, but there's more to them than you think. And so it turns out it takes a little while to explain that. So I decided to do a separate video on space-time diagrams. So that's what I'm going to do here. We're going to explain what space-time diagrams are, how they work, blah, blah, blah. So the first thing I'm going to do to explain them, it's not going to make a lot of sense at first. We got an ad playing on YouTube, on Twitch right now on the live stream, but nobody's watching, I don't think. So the first thing we got to do when we're that I'm going to do to explain this is I'm going to play a little video here, and this video is going to be about how film projectors work, which seems kind of weird, right? Why would I play a thing about how film projectors work? That doesn't make any sense, does it? Well, it doesn't make sense. So I'll play this, and please stick with me here, because this is going to make sense when it's all done. This is about 8.5 minutes, and then when we're all done with it, I'll explain why I taught you how film projectors work. Here we go.
The mechanics of the film projector. One of the most impactful pieces of engineering is the technology of movies. They've shaped every aspect of our lives. Today, of course, they're created digitally, but I celebrate here the stunning engineering that gave life to movies, the technology that tricked the mind into seeing a moving image. Film came in many sizes, from the giant 70mm, popular in the 1960s for epics like Lawrence of Arabia, to 35mm used for most feature films, to 16mm for schools, and even 8mm used by home enthusiasts. The larger the film, the greater the resolution, of course. All worked with mechanisms similar to common 16mm projectors. I'll examine this Bell & Howell 1580 16mm projector built in 1979. We'll look at the shuttle that starts and stops the film, the shutter that strategically blocks light, and the photosensor that reads the sound, all of which operate in harmony. To create the illusion of movement, a series of still images, the film, is pulled off the supply reel, threaded in between the lamp and lens so the image can be projected, then run across the sound drum, and finally coiled onto the take-up reel. However, it isn't as simple as that sounds. To see why, here's what happens if you just move the film continuously past the projector's lamp. What you see is a blur. You can just make out the images. Here's what really happens shown in slow motion. A frame appears on the screen, not moving, then the screen goes blank, and then the next frame is projected on the screen. The projector must hold the image on the screen for a moment and then cover up the image while the film moves to the next frame. Two mechanisms do this. First, the shuttle. The shuttle has 3 teeth which engage the sprocket holes in the film. The shuttle moves back to disengage from the film, then moves up, then forward to engage the film, then moves down, pulling the film with it. The film is stationary most of the time and only moves when the shuttle is moving down. This is the intermittent motion of the film necessary to avoid blurring of the projected image. Here is slow motion footage of the shuttle moving up and down intermittently. From this angle, you clearly see the shuttle move forward and back to engage and disengage from the film. 2 shuttle arms hold the teeth of the shuttle in place. In between the arms is an eccentric cam. This cam rotates with an axle and moves the shuttle arms up and down. The outline of the cam has a constant width so that the distance between the arms doesn't change. The cam shape holds the shuttle steady at the top and bottom of its travel. To see how the shuttle moves forward and backward, let's look down from above. The shuttle arms act like a third-class lever. They pivot on one end, and at the other end, a spring force pushes them forward and an effort forces them backwards. This backwards effort is created by a disc tilted a few degrees off of the axle. When the axle turns, the disc wobbles. A horizontal post connected to the shuttle arms is pressed into contact with the wobbling disc by the spring force. As the axle turns and the disc wobbles, the shuttle arms are rhythmically pressed backwards. This movement is synced with the eccentric cam to create the required motion of the shuttle. The shuttle transports the film so that it's stationary most of the time and quickly advances to the next frame. Though it is rapid, the film movement will still cause blur in the projected image. The blur is eliminated by a shutter. The shutter is a disc with a blade that protrudes from half the circumference. The other half is open. The shutter rotates once every frame and is synced so that the shutter blade blocks light from the lamp while the shuttle is advancing the film. This prevents the projection of film motion on the screen. The film passes by the lamp at 24 frames per second. At that rate, the human mind blends the still frames into fluid motion. A projector with a single bladed shutter blocks light from the lamp once every frame. So half the time, every 24th of a second, the screen is dark. This switching between a bright projected image and darkness is called flicker. If the flicker occurs at about 60 to 70 times per second, the bright flashes fuse together and appear, to the human eye, continuously bright with no periods of darkness. This rate is called the flicker fusion threshold. Since 24 flickers per second is below the threshold, the flicker is visible. This flicker is the origin of the term flick as slang for movies. But modern film projectors don't have this problem. How did they fix it? Originally, shutters had a single blade that covered the advancement of the film with an open section that showed the picture. Modern shutters have 3 blades. The first blade covers the film motion. The second 2 blades block the light even when the film is stationary. They only serve to increase the flicker rate. The 3 openings allow the image to be projected half the time. Here I've labeled the 3 blades with 1, 2, and 3 dots. Notice that the shuttle moves downward only when blade number 1 blocks the light. The 3-bladed shutter is a simple and inexpensive solution that works well. The frame rate stays at 24 frames per second, and the flicker rate increases to 72 flickers per second, above the flicker fusion threshold, so the movie appears to move smoothly and without distracting flicker. This means if you watch a film in slow motion, you will see a single frame is flashed on the screen 3 times before the next frame appears. A subtle but important detail of film projectors is the film loop. The loop allows for 2 kinds of motion of the film, intermittent and continuous. The key is they happen simultaneously. The film must pause in front of the lens to project without blur, but must also move continuously for the proper playback of the sound. The top sprocket pulls the film from the supply reel continuously. A loop of slack film starts to form. This slack allows the shuttle to quickly advance to the next frame without tearing the film. A second loop of slack film at the bottom also forms. The bottom sprocket pulls the film continuously. This is important because it allows the sound to be read correctly. Sound in movies is recorded optically on the edge of the film. After the film runs past the lamp, it runs across the sound drum. To read this optical soundtrack, light shines through a tube with a slit. This concentrates the light on a small section of the film soundtrack. A photosensor on the other side of the film measures the amount of light passing through the film at a given time. The photosensor converts the amount of light transmitted into current, and this current drives the speakers. A soundtrack that oscillates slowly produces low-frequency sounds. If it oscillates more rapidly, it will produce higher frequencies. The volume is determined by the amplitude or width of the soundtrack. Louder sections are wide, and quieter sections are thinner. Because the image is projected here, and the sound is read down here, the soundtrack is offset 26 frames ahead of the picture in 16mm films. This offset ensures that the picture and sound are correctly synced. To me, the most beautiful aspect of the film projector is how all the mechanisms are synced. The mechanisms are driven by a single rotating axle. The axle rotates the shutter and simultaneously turns the cam and advances the film. Behind the shuttle is a worm screw that drives two gears that are coaxial with the top and bottom sprockets. So this means that with every rotation of the axle, the shutter blocks and flashes light 3 times. The shuttle pulls down a single frame, and the worm screw rotates the gears and sprockets 1/14 of revolution. Since there are 14 teeth on a sprocket, the top sprocket moves 1 frame worth of film from the supply reel, and the bottom sprocket pulls 1 frame through the projector. This setup keeps all the important mechanisms in sync. One thing to keep in mind is that film projectors were designed and built in parallel with film cameras. In fact, in many respects, the technology in both cameras and projectors are nearly identical. I'm Bill Hammack, the engineer guy. Thank you to our advanced viewers who helped shape this video.
Will you help us make our next video? Will you become an advanced viewer?
Go to engineerguy.com/preview to sign up. We'd love for you to join us.
All right, so that was a little thing about film projectors, how film projectors work, and it directly applies to what we're going to talk about almost. That was you notice that they released that on Creative Commons, what was 4.0 I think, which is the same license I use. So thank you guys for making that available for everybody to use and see and learn. One of the so you get how the projector works, right? It's frame by frame, blah blah blah. You probably already knew that, but I thought that was a very cool presentation. There were some details in there that I didn't know about or had forgotten about or whatever. One cool thing that has nothing to do with what I'm really talking about today, or very little to do with what I'm talking about today, was this this idea that the film is going through the they got to get the sound right, which is a continuous thing, right? And then they have the picture, which is a frame by frame thing. And I just thought it was so cool how they did that, how they put a loop there so that that would kind of buffer the frame, and the frame would go one by one, but the audio that they pick up, it needs to be continuous, and that goes continuous. And when I saw that, I thought, oh, that's kind of a perfect analogy to the dichotomy that we have in physics between the relativity, which is general relativity, which is a continuous type thing. In general relativity, space-time is a continuous thing, and in quantum physics, it's more about particles and individual things, and and they haven't been able to figure out how to bring those together yet. But I thought that was kind of cool that they had a projector. In the projector, they have that's kind of an analogous thing, right? They got a continuous audio that has to be done at the same time that they're doing the frame by frame thing. The way they did it is to put a little buffer in there. So I thought that was kind of cool. There's a thing in a theory in physics about a projection of a higher dimension, say a fourth dimension of space, that gets projected down, that we get to see that is a way of resolving some stuff. So that's another thing. Anyway, so that's the way projectors work. Okay, and I'm going to use that to explain how the space-time diagram works. And the way I'm going to do that, oh, good, it worked. Great. So here's a film strip, right? This is just a small section of a film strip, and it feeds from the bottom, right? So you get it comes in on the bottom here, and it moves a little bit at a time. Can you see my little cursor? Good, you can see it. So you get a frame here, frame here, frame here, and each frame is a little bit different, right? Let me zoom in a little bit. So I'm going to start on the bottom here. Right, so it shows this frame. And you remember in the little films there, they explained it, right? It shows a frame and it covers it up and it quickly slides it down and it shows the next one and the next one and the next one like that. And the image here moves a little bit each time. An important thing on these images to realize is that this is two dimensionals, right? This is a two-dimensional image, which is representing three-dimensional space, right? Right. We live in three-dimensional space. Right. That's how we experience things. These are two-dimensional. They're taking a three-dimensional, forward and back, left and right, up and down, and they're getting it down to two dimensions, just up and down and right and left. And it kind of looks three-dimensional. It tricks our mind a little bit. We kind of see three dimensions when we look at it, but it's two dimensions, up and down and right and left. And then there's another dimension because they're running it through a projector. There's a time dimension. So it's three, right? It's space-time, but it's a three-dimensional. It's two dimensions of space, up and down, right and left, and one dimension of time, which is represented by these things, 24 per second going through this projector and moving a little bit each time. Now, let's imagine that we've got these this guys taking a picture, right? We're looking at this from our reference frame. We're the camera, okay? We are the camera, and we're looking at this. We're taking a picture here, and let's suppose a little fly or a bumblebee, bigger thing. But let's say a bumblebee comes in here, and he decides that he wants to photobomb our picture. So we get a little bumblebee, maybe right down here in the corner. Can you see that? Yeah, you can see that. And he comes in, and he goes, and he flies in here a little bit, and then flies back out. Okay. So the bumblebee photobombs our thing. All right, he comes in, flies in here, and then flies back out really quick, right? Just takes less than a second for him to come in and mess up our, our film for us. Now, so the way that would show up on our film, once we got it back and got it developed and everything, what we would see is we would see a dot, here. Let me make this a little bit bigger here so we can see it. We'd have a dot here, right? And the next frame, the dot would be here. And in the next frame, it'd be here. You see how that would work? Pretty simple, right? You get that, right? How that would work? And here, and here, and then the fly decides to, right, just after he messes up our thing, he decides to go back, and it goes a little bit back, dot here, and here, and here, and here, right, and then that's it, right? So when we're looking at this on our film, when we're watching it on our film projector, it's going to have that. It's going to look like the thing is moving, right? So you get a little bumblebee here. He flies in, and he moves over a little bit more, a little bit more, a little bit more. And then flies back out again out of the scene. And when we see that, it's just going to be, we're going to see it as exactly what it is, a little fly or bumblebee or bug or whatever flying in, and he'd be flying in, flying back, on the thing, and that's how we would see it. But he's only flying on the bottom of the picture, right? He's not flying all over here. He just happened to fly just on the bottom here. He flew in and flew back, right? And if all we were interested in was seeing that little bumblebee flying back and forth, we wouldn't need all this, right? We wouldn't need this whole big picture like that. And so what we can do on this thing, let me get rid of the bumblebee picture here real quick. Get rid of the bumblebees. All right, we got him erased. All right. What we can do is instead of having this whole two-dimensional thing, the up and down and right and left, all we need is right and left. We don't need the whole thing. We don't need the whole up and down thing. All we need is right and left. If all we want is that little bumblebee. So what I'll do is here I'll grab this thing here, and I will take and I'll squish this down. So all we got is the two dimensions. We're kind of, right? I'll switch it down here a little bit. Push down a little bit more. And there we go. All right. We'll zoom in on that. Now we still have three dimensions, right? We still got up and down, but we've squished it down so it's essentially just lines across here for each of the frames. Now when the bumblebee comes in, it'll look like this, right? He'll be here, and then here, and then here, right? Like this. And then he'll come back like that, right? Now notice that the bumblebee, when we watched this film and when it actually happened, when the camera took the picture, the bumblebee wasn't flying like this, right? He wasn't flying up at an angle and then making a right angle turn and flying back like this. He wasn't doing this, right? Like this. He was just going right and left. He was just coming in here and going like that, right? So this is just a representation on the film. When we look at the film, all we're looking at is a representation of what this looks like through time, right? The bumblebee came in, he flew across over here, went about this far back, and then came back out again. And when we look at the film, we can say, through time, each one of these steps here is further along in time, right? This bottom one is in the past, maybe, and then the top one is in the future if we're partway through it. So the higher we go, the further along we are in time. So the bumblebee isn't actually flying at an angle like this. He's flying back and forth like this, right? Like that. But it gets recorded this way. And this is recorded in steps of 1/24 of a second. But real life isn't like that, right? Real life is continuous. So the bumblebee he would fly straight up like this and like that, and it would be continuous. If we were looking at this in real life, it's not, time isn't in increments like that as far as physicists know. They're still debating that, I guess. But it's continuous. We treat it as if it's continuous. Now, if we wanted to represent this like this bumblebee flying in and out like that through time, we can label these things. We can actually come over here. Whoops, that's not what I wanted to do. no, I don't want to do that either. Still learning this paint package here. No, I don't want to do that. What are we doing here? All right. There we go. All right, so we can put a label over here that exactly labels. This is your 24ths of a second, right? So we can come over here and put a label on here that actually labels those. Now I'm gonna try to dial this in a little bit, and I'll probably miss it, but so imagine we've got a label, or we've got a line here like that labels, and it's got tick marks on there for every frame. I didn't line it up exactly, but you get the idea, right? Yeah. So imagine each of these tick marks is a frame, is a 1/24th of a second. See? And we can label them if we want to. We could say there's 1, 2, 3, 4, 5, 6, 7, 8, whatever, how many ever frames that we have there. And this thing here would be labeled time, T. Did I get that? T. There we go. We could put a T over there for time, because that's what that is. That's an axis. Right? And then this other one here is space. And we don't have up and down space. All we have is back and forth space, remember? I mean, it looks like it's up and down here, but we're really just, it's one dimension now. And we can label that one if we want. And we can call that one, let's call that X. I don't know why we want, they use X. I would use S for space, but they use X for position, you know, a position, X. So we can label it. And we don't need, once we got it labeled like that, then we don't need all this stuff here, right? We don't need the film in the background. We can just erase that if we want, right? Completely. And then all we got is the X and Y, or the T for time, and the X for space. And we can, you know, draw the little guy on there, you know, the bumblebee on there, et cetera, et cetera, et cetera. So that's what that axis is. The up and down is going to be time, and it's continuous, right? We had the 24 bits at a time, or the 1/24th of a second at a time, but it's continuous. It's not in real life. It's continuous, and when we graph it on a space-time diagram, we make it continuous. The same with space, but we've changed it. We've changed it so that it's instead of 3 dimensions of space, we're only using 1 dimension of space. And let me show you this here. You see that? Yeah. So this I've added a little bit more to this one. This is so it's the same basic thing, right? We've got the up and down is going to be time, right? And the right and left is location in space. And again, in actual, you know, actual space, we're 3 dimensions, right? We've got up and down, right and left, forward, backward. But when we do put it on a space-time diagram, that would be really complicated. It's complicated stuff already the way it is. So we just put that all down into 1 dimension, just back and forth, like we did with that little bumblebee, moving in 1 dimension. You know, he moved to the right and then he moved to the left. here, 0, the origin, we put at the lower left corner of that film strip. But the origin, what if the bumblebee decided instead of the photobomb, he decided to go to the left instead? He wouldn't have showed up on our film, but we could make him show up on this space-time diagram that we're doing, right? So he could have went negative, right? If we have 0, this should be minus on here, -5, -10, -15. So that fly, let's say the fly started right here in the middle. If he decided to go left instead of right, it'd be -5, right? And 10, 15, whatever, and come back. And remember, the fly is flying down here in space, this one dimension of space. He's not flying, sideways up here or whatever. He's down here, back and forth. Now when we do space-time diagrams, we don't do flies, right? It's when you're talking, flies don't fly at relativistic speeds normally, unless something unusual, very unusual happens. Flies and bumblebees, they don't fly at relativistic speeds. Again, if you're not familiar with special relativity, go back and look at my presentation I did on that. I actually did a pretty good job on it. I'm proud of myself. I went back and looked at it, and I hardly made any mistakes. It was pretty good. So you go back and look at that, or look at it. There are dozens and dozens of different presentations on how space-time works, how special relativity works. We're not talking about general relativity on these presentations. We're talking about special relativity. So you can go back and watch my presentation a year ago, September 1st, 2024, or you can watch anybody else's. But you need to be familiar with what special relativity is. Or otherwise, from going forward here, some of this stuff isn't going to make a lot of sense to you. So, all right, let's go back to this space-time diagram now. Let's put a. So we're going at relativistic speeds here, right? If we were looking at the bumblebee, this would be maybe centimeters or inches or something, right, along here on this x-axis. But we're not. We're going fast, right? We're using rocket ships, right? Here, I put a little rock. Can you see those? Did those show up? Yeah. Let's use rockets instead, right? Rockets. They're flying through space. So they're going to go real fast. So for time here, let's go years. We could make this, right? This could be anything. This could be seconds. This could be weeks. It could be years. It could be whatever. Millennia. Whatever we want to make this scale here. Same with the x. The x could be meters, could be millimeters, could be astronomical units, could be kilometers. But what we want to do on here is we want to align these so they kind of make sense. If these was meters here, 2 meters, 4 meters, 6 meters, 8 meters, and this was years, 1, 2, 3 years, and say we wanted to draw light, how fast light would go on here, we wouldn't even see it, right? It would come like this. Let me draw this in here just real quick just to show you. If we wanted to draw light on here, if this was meters, light goes at about 300,000 kilometers per second. So even if this was seconds, we would draw light and it would just be across like this, right? It wouldn't have an angle. We wouldn't be able to do much with it. So we don't want to use meters here. We want to use a big number here. And if we use years up here, a good thing we can use here is light years. A light year, right, is not a time. Light year is a measure of distance. Is how far light travels in a year's time. A light second, we could use seconds, would be how far light travels in a second, which would be 300,000 kilometers, right? Light year is that times, it's trillions, right? It's a huge amount of distance. And it turns out if we use years along the time axis, and if we use light years across the x-axis, then time ends up going exactly 45 degrees. Because, let's imagine it goes here. Suppose we wait for light to travel 4 years. 1, 2, 3, 4. In 4 years, light is going to travel 4 light years, right? Because that's what a light year is, right? So in 4 years, it's going to go 1, 2, 3, 4 light years. And you put those two together, and there it is. Same with 6, 8, 10. 10 years is 10 light years, etc., right? So if we took a flashlight down here at the origin and we shined it directly to the right along the x-axis, that light would travel across here like that through space, and it would take time to do that. And then we chart it up here. The light isn't actually flowing here or traveling at a 45 degree angle. The light is traveling along this x-axis down here, but through time also. So the time is shown up here. And same thing. If we took the light and pointed it to the left, then it would look. Then it would diagram out like this. Right? Through time, it would go like that. And when you put those two things up there, like that, and make it a 45 degree angle, it makes a whole bunch of things a lot simpler. It makes the math simpler. It makes everything a lot simpler for when you're trying to analyze stuff. That's why they do it that way. And sometimes you'll see them put a C up here, put CT up here at the top, and that just means that they've calibrated this for light. It's just another way of saying it, that they've calibrated it for light. You know. Sometimes they'll label this years. Sometimes, like I did here, I didn't label it at all. It's kind of assumed because they almost always do it that way. They almost always calibrate it for light like that. So now imagine if one of these spaceships down here. Let me grab one of these spaceships. Did I get him? No. Oh shit. Let me try harder. Still learning this thing, this program here. Alright, let's grab one of these spaceships. Alright, copy him. There he is, okay. So, let's say the spaceship started at the origin here. Oh, also, just one other thing. This diagram is from a particular reference frame, an inertial reference frame, they call it. Inertial means not moving, at rest. From, you know, if this is our perspective, if this is our reference frame, then we're sitting here at the origin, and we're at rest, which means that we, as observers of this thing, are going to be traveling not at all, because we're just at rest, right? So this axis here, if 2 years, 4 years, 6 years go by, we're just sitting here. We're not moving. We're at rest. We're inertial. We're at rest. We're the inertial frame here. So this chart is from our perspective, and we're always along this axis. We just sit here through time going on this axis here. Now, if there's something that's moving, like this rocket here, we're going to make this rocket move here. Now, imagine we start at origin here, 0, and time starts to go by, and this rocket, it travels away from us on the origin through space. Remember, we're one-dimensional space here to make it simple. And they just travel, right, like this through space. Now, when they travel through space, they aren't going to be going the speed of light. They're going to be going at some speed slower than the speed of light. So when we chart it, they're going to be up here somewhere in this area, right? So imagine that rocket is going at 0.6 speed of light. Suppose the rocket is going at 1/6 of the speed of light. The way that would look is like that if we charted it. So if this rocket down here at the bottom, this spaceship, can I grab that? No. So if that rocket is moving, if he starts here in the middle and he moves along this x-axis at 0.6 the speed of light, they call it c, they use c for the speed of light, 0.6 c, 60% of the speed of light, then in 10 years time they would move 6 light years. You see how that works? 6, because it's 0.6. So from our perspective, if we see that rocket going at 0.6 c, 0.6 the speed of light, in 10 years it will have traveled 6 light years. And that's how that's what this represents here, this line here, this dotted line. Now, because of special relativity, you'll notice these tick marks here. In our time, we've ticked off 10 years of time, right? We've been sitting here. We're just sitting here at the origin. We're not moving. We're inertial. We're at rest. We're the rest frame. So we're always on this axis here. And we're just sitting here for 10 years watching this rocket out here moving away from us. And it will take it'll go 6 light years in 10 years of time. I got a chatter here. This is a live stream, so I get chatter sometimes. Hi, Sydney. I'm doing a tutorial here on how space-time diagrams work. Kind of technical, but hi, thank you for joining and lurking this and watching the stream here. And that's how we would represent it. Now, for us, 10 years would tick by because we're just sitting here. We're not moving. 10 years tick by. But because of special relativity, that rocket moving at 0.6 the speed of light, there's a gamma factor which works out to 1.25 gamma. And so you divide 10 by 1.25 and you get 8. So the rocket, their clock is going to tick off 8 years. So we got 1, 2, 3, 4, 5, 6, 7, 8 years. So this little line here represents all that stuff. It represents all kinds of stuff here. It represents that the rocket is heading to the right instead of the left, right? Because it's going this way. It shows exactly the direction, right, that it's headed. Shows that it goes 6 light years away from us. And it shows that it traveled for 10 years of our time from our reference frame. And it's showing that 8 years have passed for it because it's got 8 tick marks on its thing. Now, when we're doing space-time diagrams, they use all kinds of different labels and stuff like that, but you often see it use something called a prime, which is just a little like an apostrophe or whatever after the T. So time for this guy we're calling that T prime. That's all that little tick means. And the way we say it is prime. That tick mark just means prime. That's the way they say it. So for us, we're T. Our time is T. For this rocket, we're calling that T prime. Now, an interesting thing about this, I'm going to back up a little bit here. So you can get a feel for how this works, right? How light works, how it's shown on the space-time diagram, how a rocket works, the whole thing. So I'm going to back up a little bit here. When on a space-time diagram like this, each of these tick marks here is time. And that time is the same all the way across. So let me show what that looks like here, if I could get that there. So 2 years up, that two for us, from our reference frame at rest here, 2 years from now is going to be 2 years from now everywhere in space for us. All right? So this line, they call it the line of same time. So at 2 light years, that's going to be 2 light years here. I'm sorry, 2 years here. It's going to be 2 years here. If we go way, way, way out, 18 light years away, that's still 2 years. Right? It's 2 years. Same with 10. 10 is going to be 10 years from now is going to be 10 years from now, no matter where we are in space. Even if we go the other direction, right? Even when we went minus, even when we went to the left in the minus direction, that's 10 years, 10 years. And they got a fancy word for that. You can call it a line of same time, but they have a fancy word. They call it line of simultaneity. It's so complicated. Lines of simultaneity. These are lines of simultaneity. They call it lines of same time. And the rule when you're doing a space-time diagram is that these lines of same time always have to be parallel with the x-axis, the space axis. Right? We're using one dimension of space. So these lines always have to be parallel with the x-axis. Lines of same time have to be parallel with the x-axis. Now there's also the same thing for space. These little tick marks here of space, we've got 4, 6, 8, 10 light years of space, of distance from us. So these are lines of same place, or lines of same location. So here's 5 minus 5, this would be, because we're going back, here's origin 0, 0, we go back here, minus 5 light years this way. That's where this location is. And this line represents that line of same location. So it doesn't matter what time it is. It could be 10 years from now. That location is still going to be the same. It's going to be 5 light years. Minus 5 light years back. See? So they call these lines the same location. You could call them lines of same place, whatever. But these are lines of same location. And the rule on these lines in space-time diagrams is that they always have to be parallel with the time axis. See that? How they're all parallel with the time axis. That's the rule. So lines of same time have to be parallel with the time axis. Lines of simultaneity, lines of same time, have to be parallel with the x-axis, the location axis. Okay, that's the rule. Now you notice these two axes here are at 90 degrees, exactly 90 degrees. But turns out they don't have to be that way. They don't have to be 90 degrees. We can make them any degree we want to be. We can make those if we wanted to. Like this. We can make the x-axis tilted like this. And a t-axis like this. Here's the origin. They don't have to be. We can change the color too. Look at that. They don't have to be exactly 90 degrees like that. But there's another rule on that, and that's that let me bring up the base axes here so you can see what's going on here. However much we tilt that here, how many ever degrees we tilt this one, we have to tilt the X one the same number of degrees up, back towards it. So that's another rule, right? When we're building these things, we have to make sure that how much ever we tilt those axes, they have to be, the other one has to be tilted the same number of degrees. And let me see if I can bring up I'm going to try to bring up a little video here that kind of demonstrates that. All right, this is going to take a second for me to bring this up because I'm kind of confused here. All right, camera, let me shut off my camera. And there we go. Okay. So you see, here's a little animation that shows you that. Same thing that we were just talking about there. However much you tilt this time axis, you have to also tilt the x-axis if you wanted them to be different than 90 degrees. And so you may ask, well, why would you want to make it different than 90 degrees? Well, I'll explain that in just a second. But just notice how they're at the same angle. Notice how that when it goes to the minus direction here, this one goes down. See, it gets bigger that way. See how that works? How much ever you tilt the t-axis, you got to tilt the x-axis up the same. And we have a really good reason for doing that too. There is, believe it or not, there is a really good reason for tilting it like that. So let me go back to this paint thing here. That show up good. The reason why we want to have these tilted like this and why we would want to put them on this same thing is that sometimes we want to represent two reference frames in one space-time diagram. We have been showing up until now our reference frame at rest. We're looking at a rocket going, or a bumblebee or whatever. It's from our reference frame, right? It's from us being at rest. We're sitting there at 0, 0. And as we go through time, we go through that, that x-axis up there, like that through time. That's us on this axis from our reference frame. Now, if we want to show things from the rocket's reference frame, remember the rocket down here? Can I grab that? No, it's not going to let me grab that. If we wanted to show it from the rocket's reference frame, the rocket's reference frame is here along this T prime axis. And because of special relativity, that rocket, the clock on the rocket is slowed down. It's going 0.6 the speed of light. And there's a little here. I'll show you this. I'm going to show you some math here, so don't get scared. If I can find it here. This one right here. This is the equation that you use to figure out gamma, which is how much the factor that the clock on the rocket is going to be slowed down. And I'll just do this because this will just take a second. This is math. If math is not your thing, this will just take a second. It's not that big of a deal. All right. Because we've got this thing calibrated so that years is light years on this one and light years on this one, and because light turns out to be 45 degrees on our chart, that means that light, c, the speed of light is 1, right? We go 1 year, we get 1 light year. Speed of light is 1 on this space-time diagram, which makes a lot of these calculations a lot easier, right? If you're looking at this calculation right here, which is how we figure out the gamma, these are Lorentz transformations, all these things. c squared is going to be 1. That's right. It makes it 1, which means that this v squared is going to be over 1, which is the same as v squared. So really it simplifies this thing, and all we got is 1 minus v squared on this, in this square root thing, which is it makes it a lot easier, right? And the velocity here is, right, we said the rocket is going 0.6 c, so we'll call that 0.6. 0.6 squared is 0.36. 1 minus 0.36 is 0.64, right? And the square root of 0.4, I can't do that in 0.64. I got to get my calculator for that. 0.64. The square root of 0.64 is 0.8. And 1 over 0.8 is 1.25. So that's how we get the 1.25 when I said it was 1.25. That's this thing here. That's gamma. This little squiggly thing over here, that's a Greek letter. Physicists like to use Greek letters. It's not a big deal. You don't get excited about it. It's not that big of a deal. This is the letter gamma. Alpha, beta, gamma. This is the third letter of Greek, gamma. And they use gamma for this factor, this Lorentz factor, which is used in all these other calculations for figuring out other stuff. So the rocket has a velocity of 0.6 c, 0.6 the speed of light, 60% of the speed of light. We plug that into this equation here. We get 1.25 for gamma, which means that whatever our time is, in this case, the rocket traveled for 10 years of our time. So the rocket's time is going to be 10 divided by 1.25. So the rocket is only going, the rocket's clock only ticks off 8 years. That's where we got the 8 from. So that's the math. I kind of saved you from the math when I explained it initially, but that's how we got it, right? That's how we got the 8 there. And all that goes back to special relativity, which again, you gotta go back and learn about special relativity. And I explained that on September 1st, 24. You can look that up on my VODs or anybody else's VOD that does a decent job explaining special relativity should be able to explain that to you, how that works. And it actually all goes back to the Pythagorean theorem, because the reason why the clock goes slower is because things happen. You know, if you want to show a light clock that's bouncing up and down inside that spaceship, if the spaceship is just sitting still, the light only has to travel this far. And according to special relativity, light is the same speed for all observers, which we observe it to be that way. If somebody's moving, then the light can't just go straight up and down. The light has to take a longer path, and therefore clocks run slower. No, that's not the full explanation. If you don't understand special relativity, you got to go back and learn about special relativity. But that's why the clock runs slower. And it turns out that it's a triangle, and if you want to figure it out, how long the triangle is, then you use Pythagorean theorem, and that's where this square root, that's where the square and the square root and all that comes from, is the Pythagorean theorem. It all goes back to Pythagoras. Isn't that cool? So there you go. Now, if we wanted to, one of the cool things about these space-time diagrams is that we can put our inertial frame here, which is the white axis I have on here. We can put that on this space-time diagram, and we can also put the rocket's space-time diagram on the same thing. Their reference frame on the same thing. And the way we do that is first we draw where the rocket went, right? We explain that. This is the path the rocket took. The rocket took. The rocket is actually traveling along this axis here, but we're representing it. It took 10 years on our time for that rocket to go up here. But suppose we want to look at it from the rocket's perspective. Let's call him Rocky, okay? Let's call this guy Rocky. That's easier to say. Okay, let's say we're on Earth. We're Terra. Here, let me put an Earth up here. Here we are. We're on Earth. We're here at the origin. Rocky is on the rocket ship. Okay, Rocky travels 6 light years away, and it takes 10 years from our perspective. But let's suppose we want to, we want to look at it from Rocky's perspective. From our perspective, we're just sitting here. We're at a rest frame, and Rocky went away in a rocket ship, right? And we're just sitting here. We're in an inertial frame, and we're traveling along that time axis here, right? Because we're not moving. We're in the inertial frame. We're in the rest frame. That's our perspective. Okay? And we're watching Rocky fly away from us. And this represents how Rocky flew. But if we wanted to look at it from Rocky's perspective, that's why they call it relativity. It's relative. From Rocky's perspective, they are in the rest frame. They're sitting still. They're in the inertial rest frame, and we're traveling away from him or her, them. We're traveling away from them. They see the Earth traveling away from them, but they're in the inertial frame, and that's how relativity works. So how do we do that? How do we show that on our space-time diagram? The way we do that is we say, oh, okay, well, from Rocky's perspective, they are at rest. So we'll draw Rocky like this and say that there's Rocky at rest, and we'll call it T. We'll call Rocky's T prime instead of just T. For us, from our perspective, we're using this axis, and we're calling it T with us at rest. From Rocky's perspective, from their inertial frame, from their perspective, they are at rest, and we'll draw that along here, and we'll say, okay, this is Rocky's T time axis now. And remember, we explained how the x, when you rotate the T axis, you also have to rotate the x axis. Well, that's what we did here. This is Rocky's inertial frame for space, for location. See that? And because we've got this Lorentz factor of 1.25, because Rocky's moving at 0.6 the speed of light, space is contracted, right? There are two things that happen in special relativity, at least multiple things that happen. Two of the main things are that time gets dilated, right? So Rocky is only experiencing 8 years when we experience 10 years. The other thing is that length contraction. Distances contract. From our perspective, looking at Rocky in the spaceship, his spaceship, and the entire length of time along his path is contracted by that Lorentz factor, 1.25. So the time that it takes him to go those 6 light years away here, right? He went to that space. Then his space is going to be 6 divided by 1.25, which is 4.8. So let's see. I'm going to try to draw a line here. Let's pick a different color here. Yellow. All right. So from here, he got to this point here. Took him 10 years of our time. Took 8 years of his time. He went 6 light years of our time. And it looks like he only went this far. There we go. That's kind of thick, but that's okay. But if you look where that intersects on his location axis, it goes 1, 2, 3, 4.8. There it is. Look at that. Can I make that skinnier right now? Yeah, there we go. That's a little bit skinnier. See that? So he traveled from our reference frame. He traveled 10 years, and he traveled 6 light years away. From his reference frame, he traveled for 8 years and went 4.8 light years, because that's his location axis. And that's how these things work. That's how you can represent on one space-time diagram. You can represent 2 different perspectives, 2 different, or multiple, more than 2 if you wanted to, reference frames. And here we're showing 2 of them. We're showing our reference frame here, and our time axis is here. Our location axis or space axis is here. For Rocky, this is Rocky's reference frame. That's his time axis and his location axis. Now remember when I said that the lines of same location and same time, lines of simultaneity, have to be parallel with the opposite axis. Remember I was explaining that? Let me show you that now. For Rocky's situation, I'm going to get rid of the light cone here just to make it a little bit simpler here, so we've got fewer things up at one time. All right, let's show what Rocky's lines of same location would look like. They'd look like this. So now why are they sideways like that? Why did we make those sideways? Well, the rule is, right, this is Rocky's line of location here. This X prime, right? That little notch there means prime. X prime. That is Rocky's, from Rocky's reference frame, that is Rocky's location axis. So from Rocky's location axis, this point way out here is 1, 2, 3, 4, 5, 6, 7, 8. 8 light years. So from Rocky's perspective, this point right here is 8 light years away. And his line of same location for that point is along here. And why is it tilted like that? Because it has to be parallel with the time axis. His time axis, not our time axis, right? We're talking about Rocky's reference frame here. So it's got to be parallel to Rocky's time axis. So this line here represents 8, 1, 2, 3, 4, 5, 6, 7, 8 light years away. That's what this line represents. This dotted line represents 8 light years away for Rocky. And it's 8 light years away no matter what time it is for Rocky. That's going to be 8 light years away for Rocky. See how that works? And this one here, what is this? 1, 2, 3, 4 light years away. This line represents how far 4 light years away is for Rocky at any time along his time axis. That's going to be 4 light years away for Rocky. Okay, now let's look at Rocky's lines of simultaneity, lines of same time for Rocky. Let's look at this first one down here. 1, 2, 3, 4. So 4 years in Rocky's time. This line represents 4 years from his origin. 4 years in Rocky's time. So this is the line of simultaneity at 4 years time in Rocky's reference frame. Right? So this is This axis here is Rocky's time axis in their reference frame. We've got 1, 2, 3, 4 years. So any point along this line means 4 years for Rocky in Rocky's reference frame. So if like let's say now let's put them both up there. This is a real cool part, which hopefully doesn't confuse people. But we can put them both up there at the same time, at both lines. Oops, shit, that's the wrong one. Sorry. There we go. All right, so if we wanted to find out, say, 4 light years, 1, 2, 3, 4 light years away for Rocky on Rocky's x-axis, and we wanted to see where that intersects with 1, 2, 3, 4 years in his time, that would be this spot right here. Right here. See where I'm pointing at there? That's because Rocky's line of same location goes this way, this dotted line right here, and for 4 light years away. And Rocky's time line of simultaneity for time 4 years from now runs along this line. And so we don't because Rocky's axes are tilted like that, then we don't make them go exactly horizontal and vertical, because Rocky's axes are tilted like that. And we can do the same thing for 8 years, right? 8 years in Rocky's time is right at this point on his axis. And his line of simultaneity, which has to run parallel to the x-axis, remember, his line of same time, line of simultaneity, runs parallel to his x-axis all the way along here. All right. And if we wanted to look at a location on his chart that's 8 years or 8 light years away, that would be right here. And every point along this line here, this line is same location, which runs parallel to the time axis, remember that's the rule, is 8 light years away. So if we wanted to find a point that was 8 light years away and 8 years of time on Rocky's time axis, that would be right here. That's where that would intersect. Now, I showed you 2 different points here, right? 4 light years away and 4 years of time. And 8 light years away and 8 years of time here and here. Now, here's something that's really cool. What does that mean? If I say 4 light years away and it takes 4 years to get there, it would have to be going at the speed of light, right? Same with 8. If it takes 8 years and it travels 8 light years in 8 years, that's the speed of light. So these 2 points here are representing something that's going the speed of light. Now watch this. I'm going to turn back on the light cone. Look at this. Hopefully I drew this. See that? It intersects exactly where those 2 intersections are. Isn't that cool? Isn't that cool the way that works? The light is traveling exactly through those intersections of Rocky's lines of simultaneity and lines of same location for what we thought light would be, right? 8 years at 8 light years in 8 years. And it turns out that if we let me turn off Rocky's lines of simultaneity and location. Let me turn those off, and I'll turn on going back to our perspective now. This white axis here, which is at right angles. Let me turn those lines of simultaneity and lines of same location on. And look what happens. The same thing happens. If we look at 8 years for us and 8 light years away for us, and follow those along where they intersect, it's right where light is. Look at that. See that? Or 4 years for us in our rest frame and 4 light years away for us, that intersects right where light is, because light travels, right, 4 light years. It takes 4 years for light to travel 4 light years. So it's exactly intersecting. And the reason that this is kind of important, the reason why both of those worked for light is because light travels at the same speed for all observers. That's why that one worked out. Isn't that cool? Because light travels the same speed for all observers. So even though we looked at it from Rocky's reference frame, it was still, 4 years to go 4 light years. 8 years to go light, 8 light years for light. From our reference frame, the same thing, right? It took 4 years for light to go 4 light years. It took 8 years for light to go 8 light years from our reference frame. So anybody's reference frame, light travels the same speed. But let me shut off some stuff here. But as we see, that's not the same for everything else, right? If we look at Rocky and his rocket, from our reference frame, he was going 0.6 the speed of light. From our reference frame, it took 10 years for Rocky to go 6 light years, right? From Rocky's reference frame, it took him 8 years to go. What was that? Let me turn his lines back on again. From Rocky's perspective, it took him 8 years to go 4.8. Isn't that what we had? Yeah. I don't have it on here exactly, but it was different, right? It's different for Rocky because he's not moving at the speed of light, and we perceive each other's time. Our clocks are different, and our distances are different because of time dilation and length contraction. So that's why it's different. Everything else is different. We see the rocket moving takes a different amount of time than what the rocket thinks it takes, and we see the rocket going to different speed, going to different distance than what the rocket thinks that it went, because of time dilation and because of length contraction. But light, because light travels the same speed for all observers, it always is exactly right. So I think that's kind of cool the way that works out. All right, let me see. Let me do something, explain another thing here. We can, let me show one more thing here. The lines of simultaneity, let me put those back up here because that's kind of an important thing when we get into the twin paradox explaining stuff. So this is lines of simultaneity for our reference frame, which are parallel to the x, right? For Rocky's frame of reference, their lines of simultaneity are parallel with their x-axis, but their x-axis is tilted like that. If you notice here, if we wanted to figure out, let's see here. I don't think I was gonna do one of these, work one of these out. What you can do with these time diagrams, another thing you can do is that you can do a kind of a rough qualitative Lorentz transform just by following these lines and transform from one reference frame to the other exact coordinate. You know what I'm saying? But I don't think I'm going to do that. That's kind of we really don't need that to explain twin paradox. But you can look that up. I'll put a link to a video that explains how to do that. I'll put that in on the video when I put it up on YouTube and other places and stuff. Let's see here. All right, so this is a line of simultaneity for Rocky here at 8 years in Rocky's time. Now there's another. Imagine if instead of going this direction, the rocket went that direction instead. Okay. So let's shut off the rocket here going that direction. Make him go that direction. We'll shut off his lines of simultaneity. Now, if he went that direction, then this x-axis would have to be different too, right? So we can't use that x-axis. We have to use an x-axis that's going this way. Remember that little video that I showed? This angle has to be the same, right? So if the rocket goes in the negative direction, goes this way, along this axis, then through time, right? Time only goes forward as far as we know so far. We have to go up, right? We can only go up in time. It's gonna look like this, right? It's gonna be in the negative direction. I called that T double prime. You know, it doesn't matter. It doesn't matter what you call it. But its x has to be the same angle here. This angle has to be that angle. And by the way, there's a way to figure out what that angle is using some trig that I'm not going to do. But when you get into how all of these transformations work and stuff, you kind of intuitively get that okay, this is a tangent of a ratio over here. This is the space axis for Rocky heading in that direction. This is the time axis for Rocky in that direction. Now let me show you what the lines of simultaneity are for Rocky in this situation, and they look like that. Now they're tilted differently. Remember when he was the other way? Here, let me show you back. Let me get back up here. I'll show you what it looks like the other way again. When he was this direction, his lines of same time went tilted this way. See that? Because we wanted to make it parallel to the x here. This x-axis. So they're tilted this way. See that? They go from lower left to upper right. See? But when we change his axis to going that way, and he's got an x-axis that way, his lines of same time go this way instead. See that? They go from lower right to upper left. And the reason they do that is because they have to be parallel to the x-axis here. This x double prime axis, which goes along with him if we wanted to talk about his reference frame heading in this direction. Okay, so let's say he's going 0.6 c, 60% of the speed of light, and from our reference frame it takes him 10 years. He gets to this point, which is kind of 6 light years in that direction, right? 0.6. And this time for him, it takes him again 8 ticks here. His clock is ticking slower, so it's 8 years for him, for his time. And it takes 4 years, right? It takes 4 ticks here instead of 5. So from our reference frame, it's taken 10 years. From his reference frames, it's taken 8 years. And for him, everywhere along this line is 8 years for him. And that line would extend all the way down here too also, parallel to this x-axis. Same at 4 years. 4 years for Rocky. That's a little bit less than 4, it looks like. But everywhere along this line then would be that time for Rocky. And it's tilted in this direction. Right? Which is different than if he's going this direction. If he goes this direction, the lines of simultaneity, the lines of same time, run this way. If he's going this direction, the lines of simultaneity, the lines of same time, run that direction. So it's different. It changes depending upon what direction he happens to be going. So that's kind of cool, isn't it? Now let's see. There was something else that I wanted to explain here. Yeah, I don't think I need to do that. It's kind of complicated. I think people are already confused enough. Anyway, there's a lot more. I wanted to explain this because there's a lot more to these space-time diagrams than what you get if you just watch a video about twin paradox. You're going to miss it, right? Unless you understand what's going on with those time diagrams, space-time diagrams. The explanations that you hear about the twin paradox are going to not be totally, explanatory of what's going on, and you could get confused. So this is something that you really need to understand how it works. Is how these space-time diagrams work. Let's see if I can. I was going to see if I could. Yeah, this would be kind of complicated, but I'm going to go ahead and try to explain it anyway. But that's okay. Let's see here. All right, so if we're looking at Rocky's, all right, let me get rid of this one of him going, because he can only go one direction at a time. Whoops. There we go. And that one. And we'll make this one visible. There we go. All right, so if he's going this direction, it takes him 8 years to go this direction. So from his, this is what I wanted to explain. Remember, from our perspective, from our rest frame, it takes, and we're watching Rocky, right? And we're just sitting here in our rest frame, our reference frame, our inertial frame. Those all mean the same thing. Inertial, rest, that means the same thing. We're not moving from our perspective. And we just sit here for 10 years. We're just riding along this axis here. We get 10 years from now. We see Rocky going that far, right? Which is 6 light years away. In Rocky's time, he's only going 8. Now suppose we wanted to show that Rocky was actually going 10. Right? Suppose we want to look at this same situation from Rocky's perspective. From our perspective, we went 10 years. We saw Rocky go 6 light years away, and we from our perspective, we saw Rocky's clock tick 8 years off his clock. Okay. Now, from Rocky's perspective, they're seeing their clock tick off at a normal speed. It seems to them that their clock is ticking off at a normal speed. And they've gone along 8 years at this point. So let's suppose we want to look at things as if Rocky, from Rocky's perspective, now Rocky thinks that Rocky is in a rest frame, right? And Rocky's in an inertial frame. Rocky thinks Rocky is at rest, and we're the ones that are moving. So let's look at that. Sure, this is going to take just a little second here as I grab this. And I'll grab this extra little 2 year. Here are extra 2 years I had set aside just so I could explain this. Just took me a second to remember why I put that there. All right, so we got here's an extra 2 years for Rocky. we'll stick that over here. So Rocky can travel an extra 2 years, okay? I don't know if I got that very well there, but it's gonna be off by a little bit, but that's okay. You understand. All right, so let's say we're in the rocket ship with Rocky, right? We're in Rocky's reference frame. Now Rocky goes 10 years, right? Rocky's at rest, and he goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 years. Okay. So this point, this line here, this line of simultaneity, line of same time for Rocky, from Rocky's perspective, in Rocky's inertial frame, is 10 years. So everywhere along this axis here is 10 years of time for Rocky. Right? And remember, that's got to be parallel with Rocky's x-axis. And look at what happens here. Look at what happens for Rocky. All right, so we're in Rocky's reference frame. We're sitting there for 10 years. 10 years go by, and it looks, from our perspective, it looks like the Earth has gone away, right? It looks like the people in this reference frame have moved away from us because we're in the rest frame. See how that works, right? And so what we see is 10 years of our time. We follow that line down here to see where it intersects with the Earth frame. Look where it intersects, 8. See that? So from Rocky's perspective, Rocky sees 10 years go by, but he sees only 8 years go by on our clock. See how that works? But from our perspective, let me flip this back here. I know this is kind of confusing, but it's cool. It is. From our perspective now, let's go back to our perspective now here. We went 10 years, and these are our lines of simultaneity, right? Because our lines of same time have to run parallel with our x-axis. 10 years of our time, we go across there. It intersects with Rocky's 8 years. 1, 2, 3, 4, 5, 6, 7, 8 clicks. So you see how that works? If you're looking at the perspective, say we're on Earth, right? We stayed on Earth. From our perspective, we're at rest. Rocky takes off at a rocket ship, and we see Rocky going at 0.6 speed of light. From our perspective, 10 years goes by, and we see 8 years tick off on Rocky's clock. From Rocky's perspective, Rocky's in the rocket ship. Rocky thinks that they are at rest. They see the Earth going away at 0.6 the speed of light. 10 years tick off on Rocky's clock. But when Rocky looks back at Rocky's line of simultaneity and looks at how much time has gone by on Earth, Rocky sees 8 years go by at Earth. And this kind of gets at the heart of the paradox, right? Because from Rocky's perspective, Rocky says, 10 years have gone by for us, but 8 years have gone by for Earth. So Earth is younger. The twin on Earth is 8 years, is only 8 years gone by. 10 years have gone by for us. But you flip it around to the perspective of the person on Earth, They think they're the ones who's sitting still, and that the rocket is going at 0.6. The people on Earth say, okay, 10 years have gone by for us, but only 8 years have gone by for the rocket. And that's what's kind of weird. Both of them see each other as younger in that situation. And the way that you get around it, and you say, how can it be? How can both of them, how can both the twin on Earth and the twin in the rocket both see each other as younger? And it turns out that it has to do with where they are in location. And I'll explain that on the next video. But isn't that kind of cool how that works? Let me light those back up again, because that's kind of cool. Same with time. There we go. I know it looks kind of confusing here, but I explained it, right? It makes sense, right? So Rocky goes 10 years to here. His line of same time intersects 8 years for us for the Earth reference frame. Looking at it from the Earth reference frame, 10 years tick by on Earth's line of simultaneity. Earth sees only 8 of Rocky's years go by. So that's the heart of the whole thing. And we'll, on my next stream, I'll do that tomorrow. I guess I'll do a stream on the actual twin paradox, and we'll go through all the details of that, how that works, and explain why that is and how that can be, and the reason, and it's true that, and it's absolutely true. That's what's going on. From the Earth's perspective, Rocky is 8 years past for Earth's 10 years, and in Rocky's perspective, 10 years have gone by, but only 8 years have gone by for Earth from Rocky's perspective. And the way that they get away with that is that Rocky and Earth are in 2 different inertial frames and 2 different locations. 2 different locations. That's what makes the difference. So that's how that works. So that's how space-time diagrams work. And I won't go through these all, but I'll just explain them really quick here. These are the Lorentz transformation equations, and these just explain how you translate between different locations. So you can just pick any arbitrary location here, and if you want to figure out x prime again is one reference frame, x prime and t prime is one reference frame, t and x is another reference frame. This little triangle here means delta. It just means a change in location. If we're always referencing from the origin, then you can get rid of that and just use the t and the x here. So if we were in an x and t location here on our chart from the x and t reference frame, and we wanted to translate that to figure out where that is on the x prime and t prime, we would if we're trying to solve for x prime and t prime, then we just plug into these equations here what our t is, our t location, and our x location, and our x location and t location here. Multiply that by this gamma, which we figured out down here with this equation, which in the case of 0.6 speed of light is 1.25. So you just plug them in there and solve that equation, and it will tell you what the coordinates are. So you can transform. You can do a transformation between one coordinate system, one reference frame, to the coordinate system of another reference frame. That's all those are. All right. Any questions? I don't think anybody's watching. I blew through the commercials here, the ads here on Twitch. This is a live thing, right? And I just blew through the ads, so people were missing parts of this. So they're going to have to, if they want to actually follow along and figure this out, they're going to have to watch the VOD along with everybody else. So, all All right, that's it for that. So today is the 17th, September 17th. Happy Constitution Day. It's Constitution Day. I think I was going to do a stream on the Constitution, and maybe I'll still do that. Maybe I'll take some time, or take rest for an hour or so, and do another stream on the Constitution, because I want to talk about that today too. But I wanted to get this space-time diagram thing out there. So if you have any questions, you can type them into the YouTube, I guess, YouTube comments or whatever. I will put a link to this to another video of somebody who explained how to do those translations if you want to get into the math part of it. But really, that's about it on the thing. I think I covered everything that I wanted to cover on that. I'm going to check really quick here. Make sure I didn't miss anything. I don't think I missed anything. I think I covered it pretty good, but I'm going to check really quick here. Because I did make some notes here that I wanted to follow. Let's see. All right, we explained how projectors work. Squished them up, did that. Lines the same location, talked about that. Spaceship timeline. All right, yeah, I think I covered everything. Great. All right, so the next one we'll do the twin paradox, which is really cool. But you had to know how these space diagrams worked in order to understand how I'm going to explain the twin paradox. And you have to know how special relativity works in order to know what I just explained here on. So if you don't know any of this stuff, and this was just, you didn't understand what I was just talking about, go back and watch the video that I did on September 1st and 24, where I explained special relativity, and try to understand that. And you're not going to understand it the first time because it's complicated. It's hard to understand. It's not intuitive. So try to understand special relativity first, then understand how space-time diagrams work, and then we can explain how the twin paradox works. So I'll do that next time. All right, I appreciate everybody coming by and watching my video. Yeah, follow me. What do I do? Follow, subscribe, click like, comment, whatever. Help me with the algorithms. I'd appreciate it. All right. All right, let me play my closing here, everybody. Thank you for watching. Take care. Bye.